Hi, and welcome to our next unit here in our chapter on information theory. So this is on the Kullback-Leibler divergence. So here we'll discuss that the Kullback-Leibler divergence can be seen as something like nearly as a distance between distributions, not exactly. We'll also discuss that it can be understood as an expected log difference. We'll discuss a little bit how it can be used in order to fit one distribution against another one, and that it also has quite a strong connection to the likelihood ratio. Okay, so let's start out with the definition, or I guess two definitions. Let me actually move a little bit so you can see that. So you can see the slide number in the corner. So, okay, we want to establish now KL as a measure of a distance between either discrete or continuous distributions. I will now assume that these distributions have the same support, okay? So I'm going to already write that with a capital D for distance, dKL. You'll see that it's maybe not exactly a distance because it's not really symmetric, and I'll use this double bar Q here. So I'll read this out as the Kullback-Leibler divergence between P and Q, and as we will see in a few seconds, order does matter here. So the definition now is that this is the expectation of log of P of x divided by Q of x when we take the expectation with respect to P. So as before for entropy, basically the random variables that we are assuming that exist. Yeah, so maybe there's a random variable x which is distributed with P, and a random variable y which is distributed by Q. They don't really matter, so it's basically a measurement between densities or distributions. And so it's log of P divided by Q when we take the expectation with respect to P. Okay, so we can write this with the sum for discrete random variables or discrete distributions, and we can of course write this with an integral with respect to continuous distributions. And there's a bunch of stuff we need to, I don't know, talk about for a second, for like conventions for when things go to zero. So I'm not going to read this out. So yeah, just maybe take a look at this in your own time. It's not that important for now. I mainly now want to make this point, or want to discuss what actually the intuition behind this formula is. So why are we looking at this weird thing here? So I actually want to do this a couple of times and connect this understanding new things. If we want to understand new things, it's always a good idea to connect that to stuff that we already know. So the first point I want to make is that, yeah, maybe we can see this as some form of a distance. Well, for it to be a distance, I guess we have to establish a couple of properties. The first properties is it does not have, in order for it to be an intuitive distance, is that this formula is pretty obviously not symmetric. So very often we think about this as some distance between a distribution P, where P is like something we sample from, like the true distribution of the data, like the original form of the data, and then Q is something we approximate this original distribution with. And then we want to measure the quality of that approximation. Yeah, so, and we do that with reference, and that's the important point now. We do that with reference, or in expectation with reference to the true distribution. So maybe for this to become a little bit clearer, let's go through a couple of example calculations. So here, let's assume that our original P distribution is just a standard Gaussian, univariate, so zero mean, variance of 1. And our Q is a Laplace distribution. And now we apply the Kullback-Leibler between P and Q. We calculate this. And I've also tried to visualize a little bit here how this calculation now works out. So here we can see how the two distributions look like. So our Gaussian and our Laplace. We now calculate the ratio of the densities. I'm not sure whether this helps, but I just want to visualize a little bit how the computation works step by step. So we calculate here the ratio of the densities. Then we do a log of the ratio of the densities. And then we multiply that with P, integrate everything out, and we arrive at our Kullback-Leibler divergence between P and Q, which is here 0.21. And I guess if you want to do this yourself, either in R or Python, maybe try to calculate. Write a little program to calculate that for two given densities. Here's a further example. So now we calculate, well, the only thing we now change in the example is the order of the two densities. So now P is our Laplace as before, and Q is our standard normal. And here we again have the two densities, and that's the same as before. They just swap colors. So blue became red and red became blue. Now we calculate the ratio of densities. Well, that already looks different. We now do log ratio, still looks different. So maybe we are lucky if we now multiply it with the P density and then integrate everything out. Maybe we get the same Kullback-Leibler. No, we don't. And it's also somewhat obvious from the formula. It's just can't say much more about this. Just doesn't work. It really depends on the order of things. So we need to be careful about this. Here is a further variation of what we did. So I will now, as before, use the standard Gaussian for P, and for Q, as before, I will use Laplace, but I will now use different values for the sigma parameter of the Laplacian. So here here's a fairly peaked Laplace. Here is a somewhat medium-sized Laplace, and here is a very flat one. And we can see here the Kullback-Leibler. So this is 1.65, this is 0.64, and this is 0.21. And you can see for the Laplace, which is the kind of best approximation, at least among these three guys, Kullback-Leibler here is the smallest, and we'll see what we can do with this in a couple of minutes. Okay, and we'll just let's keep it at this simple calculation here for now. Okay, that this is not symmetric is maybe not so great. So can we at least establish that this quote-unquote distance between two distributions is non-negative? I guess it's going to become quite weird if it can become negative. Turns out that there's this information inequality principle, and we can really now show that Kullback-Leibler is always 0 or larger, and it becomes even nicer that it will be exactly 0 if and only if P equals Q. Can we prove that? Yes, and that's actually quite simple. So let's do that, and we can do that simply through Jensen's inequality. So let A be now the support of P, and as we are always assuming when we calculate Kullback-Leibler, then that the support of P and Q are the same, so I guess A is also the support of Q. So I'll start out by considering minus Kullback-Leibler between P and Q. We can write that down by simply plugging in the formula. We can now draw the minus sign to the inside, which simply means we can draw it to the inside of the sum, but we can even draw it to the inside of the log function, which means P and Q swap places. So now it's not P divided by Q, but it's Q divided by P. Okay. And now the interesting thing happens. Because our log here is a concave function, we can draw this to the outside when we apply Jensen's inequality. And after we did that, P cancels out with P. We sum over Q. Summing over Q is just 1 because it's the density. And we end up with log of 1, which is 0, which means we now know that minus Kullback-Leibler is less than 0, which means Kullback-Leibler itself is equal or larger than 0, and that was exactly what we wanted to show. As log is also strictly concave, we know that from Jensen's inequality, we also know that equality can only happen if this quotient here, q divided by p, is constant everywhere. And that can only happen if p equals q, because both are densities. And yeah, I've written this down here for the discrete version, but it works exactly the same for the continuous case. Okay, great. So let's move on to further interpretations now of Kullback-Leibler. So we can now, our first interpretation is Kullback-Leibler as a log difference. So let's assume that we have some data in front of us and that that data is actually being generated from some unknown distribution p. And we now model p by using some approximating distribution q. So the first thing we could simply do is we could simply see Kullback-Leibler as the expected log difference between p and q. So we could say that we take the log of p minus the log of q, and now we take the expectation with respect to the distribution that our data has, which is p of x. Yeah? So this is where we actually integrate out with respect to our data distribution, because we integrate out with respect to the truth. And then a good approximation q should actually minimize this difference to p in log space. So here's again a visualization and a calculation. I hope that helps a little bit. So again, let's take our original distribution to be a standard Gaussian. Let's take as an approximating thing, again, the Laplacian. So we can now, we did this calculation before, but we now do it on this, in this log space as a difference. So we don't compute the ratio, we compute the difference on log space. So here we have the densities, that looks exactly as before. And now we take the log of both, and then we compute the difference. And now we take the expectation, with respect to p, and get our hands on the Kullback-Leibler, which I think we have seen before as a value. Let me check that. 0.64, did we do that? Yeah, we did that here. Yeah, so that's the same thing. And I guess we didn't do this. We had different parameters here, but it's this calculation here. Yeah. Okay. So what can we now do with this? Well, what we very often want to do in machine learning and statistics is that we want to quantify how different one distribution is from another. And we can now use KL divergence as the difference between distributions and use it as a loss function. So in our example, we very often now already investigated here p equals a standard Gaussian. So let's assume that our data comes from that, and for some, I don't know, weird reason or whatever, we want to only approximate that with a Laplacian, with a zero mean Laplacian, which has this parameter sigma. And what I can now do is I can plot the KL divergence depending on sigma between all of these Laplacian distributions here and my standard Gaussian. Get a curve like this here, and I can identify where I have the minimum, and that I can use as the best fit, so to speak. I can even connect Kullback-Leibler further to another well-known principle in statistics, so I can connect this to the likelihood ratio test. So let's assume we have some data and we want to figure out whether P or Q matches the data better. So how do we usually do that in statistics? Usually do this through likelihood ratio. So we take our distributions P and Q and we now do a likelihood product over the complete data set. So we multiply over all of the observed, over all of the observations, indexed by I, and we divide P by Q. And if we put this on log scale, we put a log in front of this, and this then, now we can draw this to the inside, and the product becomes a sum. We have the log here on the inside in front of P divided by Q. So if now for a certain xi, we know that P divided by Q is actually larger than 1, then apparently P seems better suited to modeling this observation than Q. If we know that P divided by Q is smaller than 1, then Q seems better. Now, if we assume that data is actually generated by P, we can also ask, how can we quantify how much better P actually fits than Q on average? And the answer is, seems to be quite obviously here, this expected value of the likelihood ratio. But this expected value of the likelihood ratio that we are now computing, this formula is exactly Kullback-Leibler, and this is exactly our formula as we have introduced this before.